Greetings, we are continuing with our lectures. Today we want to look at heat pumps and refrigeration cycle. So we want to look at heat pumps, and refrigeration cycle. When we talk about power cycles, reversible ones of course, remember that heat was being supplied to a working fluid at high temperature and rejected at low temperature. Remember, for power cycles, heat supplied to a working fluid at high temperature and rejected or discarded at low temperature. So in the same way, then we can have a reverse cycle where heat is extracted at low temperature and discarded at a high temperature. We can have a reverse cycle where heat is taken at low temperature and rejected at high temperature. This is what characterizes the heat pumps and refrigeration cycle. This is a characteristic of heat pump and refrigeration cycle. So that a heat pump is a machine, or you can consider it as a unit, which a heat pump is a unit which will supply heat at high temperature, and a refrigerator is a machine or a unit which will extract heat from a cold space. So a heat pump will supply heat at high temperature, and a refrigerator will extract heat from a cold space. So that, what does this mean? It means that the definition of heat pump and refrigerator is separated by a very thin line. In other words, you can actually have a machine which can serve both as a refrigerator and as a heat pump. For example, you can have a machine which will extract heat from the cold space, and that heat can be supplied, for example, to a domestic heating unit. So the difference between heat pump and refrigerator, a very thin line, very thin line. So we can have a machine, which can serve both as a refrigerator, as a heat pump and refrigerator. So that, like I've said, it's a machine which will be able to extract heat from the cold space, and that heat can be used for domestic heating and so forth. So it's basically a thin line when we are talking about those concepts, that concept. So that in the case of power cycles, remember, in the case of power cycles, heat is supplied to that fluid, and so that fluid will do work. For power cycle, the working fluid does work. While in the reverse cycle, work is done on the working fluid. Work is done on the working fluid. In general, most of these working fluids can be either in the liquid or vapor phase. The working fluids can be in the liquid or vapor phase. The working fluid will be either liquid or vapor phase. Now, can be air. But if it's in air, normally it's used in air conditioning units, where the air serves both as the refrigeration fluid and as an air conditioning medium. In the case of air, in air conditioning plants, it acts as refrigeration fluid and air conditioning medium. So this refrigeration cycle has several flow processes, and each of these flow processes are in different components. And one of the most important things is when you talk about flow processes, think about unit processes. They're in different components. And one key thing is that we are assuming that the potential energy and the kinetic energy at the entrance of that particular component is the same as the potential energy and kinetic energy at the exit. That's a very important assumption to know. So we are saying in the refrigeration cycle, we have flow processes in different components. And important to note is that the kinetic energy at the entrance and exit of each component is relatively the same. So basically, there's no change in kinetic energy and there's no change in potential energy. We assume the kinetic energy and potential energy at the entrance and exit of each component unit does not change. Now, what's the import of that? The equations which we are familiar with. Remember, we saw that dH plus dC squared over 2 plus gdz was dq plus or minus dw, plus or minus depending on your notation. If work done, you're assuming is minus, and work done by the system is positive, work done on the system is minus, or vice versa. That will determine whether you have dq minus dw or dq plus dw. So this, remember, is kinetic energy. So we are saying there will be no change. This one also potential energy, there will be no change. So dH will be dq, according to notation, minus dw. I say that's just notation which you've used. And so for a reversible cycle, you know that is 0. For a reversible cycle, always remember that that is 0. So if you consider a reverse cycle, let's just look at Carnot cycle in passing. And I encourage you to look at our lectures. Remember Carnot cycle? For the pressure volume plot, we have the Carnot cycle, 1, 2, 3, 4, the clockwise direction. 1 to 2 was isothermal expansion. 2 to 3 was adiabatic expansion. 3 to 4 was isothermal compression. 4 to 1 was adiabatic compression. Remember that. And remember from Clausius inequality, which we have discussed extensively in our other lectures, yes, greater or equal to dq over t. So for the adiabatic processes, dq is 0. In other words, there's no heat transfer for adiabatic processes. dq is 0. Therefore, ds is 0. So that means that for adiabatic processes, that process is basically isentropic. There's no change in entropy. So if we translate these expressions, the temperature entropy diagram, we have temperature and we have entropy. So what will we have for the reverse process? For the reverse process, remember this is in the clockwise direction, so if you press the area, then you get that the value of the work done is positive. In the reverse process, we are following the anti-clockwise conformation, and so if you trace the area, the work done will be negative. So we have from 1, 2, 3 to 4, and of course in the anti-clockwise manner is for the reverse process, anti-clockwise manner. So it's very, very important for us to note. Remember, this is isentropic, that's corresponding to adiabatic processes, and of course this is isothermal, no change in temperature, and of course even the pressure, there's no change there. So for the reverse processes, step 1 to 2, step 1 to 2, 1 to 2, we will have, in this particular case, isentropic compression. Step 1 to 2 is isentropic compression, where we are moving from some low temperature and low pressure to high temperature and high pressure. Low temperature, low pressure, some high temperature, high pressure. Step 1 to 2. So 2 to 3, we'll pass through a condenser so that it will extract that heat. 2 to 3. Step 2 to 3. Through a condenser. Heat extracted. Step 3 to 4, that again will correspond to isentropic expansion. This isentropic expansion, step 3 to 4. That's isentropic expansion. So we are back to where we were, low temperature, low pressure, and of course 4 to 1 will evaporate the system through an evaporator. Go through an evaporator, step 4 to 1. Step 4 to 1. We're moving through an evaporator. So that in a nutshell, if you're talking about efficiency, remember, if you're talking about efficiency, talk about output over input. So the cycle efficiency for the refrigerator, so the cycle performance, CP, the cycle is performance. First of all, for the heat pump, the head P is heat pump. Will be given by, first step there, cycle performance, where we have for heat pump will be Q for 1 over W. And we put a negative here because in that particular case, remember, work is being done on the system, so we have negative work. Being done on the working fluid, so we have negative work. So to make it positive, put that negative there. And of course, the cycle performance for the refrigerator will be Q23 to 3 over W. Q23 over W. And remember that from our equation, we have seen that for the reversible cycle, dH was equals to dQ minus dW, and because it's reversible, dH is 0. So dH is 0, so 0 is given by Q minus W. And so what is Q here? We have Q, which is 41 plus Q 2 to 3 minus W. And of course, if you put in these quantities, remember from that quantity there, from those expression there, Q for 1 can be expressed as minus CP HP W. And Q 2 to 3 can be expressed as CP cycle performance of the refrigerator W. So if you plug in these quantities, we have 0 is equals to minus CP HP, and then plus CP W minus W is equals to 0. Of course, you can eliminate by dividing throughout by W, so we'll have minus CP HP, we'll have minus CP HP plus CP ref used to the subscript for the heat capacity, as well as heat capacity. So C dot P cycle performance ref will be equal to 0, will be minus 1 is equals to 0. And so we can say that C dot P, the refrigerator, is simply CP HP, and then of course plus 1. So very important for us to note, when you're looking at heat pump or refrigeration cycle, that's a reverse process. The power cycle is also a reversible process, but the reverse of that, in power cycle, we normally supply heat to the working fluid, but in the case of the heat pump, we are not supplying work to the working fluid. We are not supplying heat to the working fluid. We are actually extracting heat from the cold body, and we are rejecting it at high temperatures. So let's stop at this particular point. We are continuing these lectures on heat pumps and the refrigeration cycle.